Hi there, and welcome back to this Integrated Math 1 video series. Today we're going to talk about something called substitution. But before we get to solving systems of linear equations using substitution, let's go ahead and do these 4 warm-up problems. Alright, so in number 1 here it says draw a system of equations that has no solutions. If it has no solutions, think about it graphically. If they have no solutions, meaning those two linear functions never intersect. Think about two lines that never intersect. Those are going to be what we call parallel lines. So really, as long as your graph included a version of something something like this, where we have two lines that are parallel, they're never going to touch, therefore there's no solution. All right, number 2. 8% of 200. Again, we're going to multiply the two numbers involved. So 8 times 2 is 16. And so it's either 16 or 1.6 or 0.16, something like that. Let's make sense of this. 8% of 100 would be 8, right? Because 8% means per 100. So for every 100, it's 8. So 8% of 100 would be 8. So 8% of 200, which is double that, would be double 8, which would also be 16. So it kind of confirms our ideas there. Number 3, so solve for x here. One thing we can do to start to get x by itself is we're going to do the inverse operations in the opposite order of the order of operations. So typically we'd start inside here, do the multiplication, then subtraction, and then kind of work our way out. We're going to do inverse operations in the opposite order. So we're going to start from the outside and work our way in. So we're going to start with the 1/3 here. We're going to do the inverse operation. Right now this is multiplying by the parentheses there. So we're going to end up either, you can think about it as dividing by 1/3, or we're dividing by 3 essentially. By multiplying by 1/3, we're dividing by 3. So what we could do to both sides is multiply both sides by 3. So we multiply this side by 3 and this side by 3. So that's going to leave us 3 times 1/3 is just 1. So we're going to have 1 times the set of parentheses, which is just the parentheses. And then 17 times 3, let's see, 10 times 3 is 30, 7 times 3 is 21. Add those together and you get 51. All right, and now we can continue to solve this. Again, inverse operations in the opposite order, so we're going to add 5 to both sides. All right, typically multiplication comes first and then addition and subtraction, but inverse operations in the reverse order. So the reverse order, we need to take care of the subtraction first. We're going to add 5 to both sides, so this will be 2x equals 51 plus 5 is 56. And of course, we're going to do the inverse operation of multiplication, which is division. So we're going to divide by 2 on both sides, giving us x is equal to, let's see, 50 divided by 2 is 25. And then 6 divided by 2 is 3. Add those together and you get 28. So 28. And then we can always check our answers by substituting back in here for x and making sure that the two sides are equivalent. All right, number 4, what is the solution to the system graph below? Hopefully you can see the graph here, and you're looking for where those intersect. So where the two lines intersect, which by the way, the lines are down here. So they intersect at the point -2. Let's see, this is 20, so that means every one of these is negative 5 more. So -5, -10, -15. So -2, this point right here, -2, -15 is the solution. Going back to our previous video, we talked about what does a solution of a system of equations mean. It means that this point here, this x and this y, satisfy both of these equations. So if we put -15 in for y here, and -2 in for the x, let's see if this works out. -2 times 4 is -8. -8 minus 7 is -15. So that checks out, right? The sides are equivalent. Let's see if it works for the bottom one, because it has to work for both, right? It can't just satisfy one of the equations, it has to work for both. So -15 equals -3 times -2, and for x, minus 21. Let's see. -3 and -2 multiply to give us +6. Positive 6 minus 21 is negative 15, so both sides work out there. So because it satisfies both equations, it is a solution to our system. We can see it graphically here, and we've also substituted those values in to double check that. So in our last video, we talked about graphically and looking for these solutions graphically. Today, we're going to move beyond that and look at how can we solve systems of equations, such as this down here, algebraically. All right, because so far we've only looked at it from a graphical perspective. The strategy that we're going to use here, we're going to solve systems of equations using substitution. So as I mentioned earlier, that's what this video is about, is substitution. And so there's one type of technique that we can use to solve these algebraically. So let's get into it. And let's really talk about what substitution means and how we can use it. So we've got the situation here. It says, Jamie is the same age as Tim. Jamie is the same age as Heather. So what must be true? Well, hopefully you're thinking, if Jamie is the same age as Heather, and Jamie is the same age as Tim, then that means that Tim and Heather are the same age, right? This is what we call the transitive property, and really we can substitute in. If Jamie is the same as Tim, then we can replace Tim in for Jamie there because they're the same age, right? So then that means that Tim is the same age as Heather. So we've substituted Tim in for Jamie because we know that they are equivalent. So that's kind of the idea of what we're going to get into today. Similar situation. We've got y is equal to negative 2x plus 9. Y is also equal to 3x minus 1. So what must be true? Take a second. Think about it. Hopefully you're thinking, well, if y is equal to this and y is equal to that, then those quantities must be equal. So therefore, negative 2x plus 9 must equal 3x minus 1. So really what we did here is, since y is equal to this expression, negative 2x plus 9, then we can substitute that in for y here. So we can take out the y, and substitute in the 2x, negative 2x plus 9. So we have negative 2x plus 9 equals 3x minus 1. Same idea, that transitive property. So now we can actually solve this. Again, what are we solving for? We're solving for the x and y coordinates, right? Remember the point that satisfies this system. So right now we're solving for x because that's the only thing we have in our equation. So let's do that. All right, so let's go ahead and add 2x to both sides. So that's going to be 0x is over here. So it'll be 9 equals 3x plus 2x is 5x minus 1. Then, of course, we can add 1 to both sides. It'll give us 10 equals 5x. And then from there, we can divide both sides by 5, giving us x is equal to, let's see, 10 divided by 5 is 2. So the x coordinate of our point that satisfies both equations is 2. So we need to find the y value though, right? So if you think about creating our point, 2, comma, and we don't know the y yet. How can we figure that out? Well, we can substitute the value of 2 in for x up here and figure out what y is equal to. So let's see, if we substitute in for 2, x for 2 there, we get y is equal to 3 times 2 minus 1. So that'd be y is equal to 3 times 2 is 6. 6 minus 1 is 5. So the y value is 5. So the point 25 is the solution to this system. Let's check it graphically. So again, we have our two lines here. The first line has a y-intercept of 9 and a slope of negative 2. So down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1, and so on. The other one has a y-intercept of negative 1 down here and has a slope of 3. So up 3 over 1, up 3 over 1, and so on. So where do they intersect? Well, they intersect at this point here, which is the point 2, 5, just as we thought, right? So that confirms what we did algebraically. We can also substitute them back in. So if we substitute 5 in for the y value and 2 in for the x value for both equations, it needs to work out for both. So that'd be 5 equals negative 2 times 2 plus 9. So in this one we get 5 equals negative 4 plus 9, and that means 5 equals 5. That's a true statement, right? Both sides are equivalent when y is 5 and x is 2. Let's check it for this one. When y is 5 and x is 2, we get, I'll do this in maybe red, so 5 equals 3 times 2 minus 1, so that's going to be 6 minus 1, and you get 5 again. So it's also equivalent. Now it's just a coincidence, though. I want to make sure and point this out. It's kind of a coincidence that both have 5 equals 5. There are other situations in which it won't be the same number. Up here in the first equation that's equal to each other, and the same thing down here. So you might have 5 equals 5 up here, but then like 7 equals 7 down here or something like that. But as long as they're equivalent, then it satisfies both, and we're good to move on. So that satisfies both of those equations. All right, so let me give you a second to try this one. Kind of similar situation, so take a second and see what you can do on this one. All right, so in this one, same thing. If y is equal to this and y is equal to that, then therefore 8x minus 25 must be equal to 11x minus 7. By substituting this in for the y down here, or you can think about it as substituting this in for the y up here. Either way, using substitution, we're setting up this equation now. So we have, let's go to subtract 8x on both sides. So we get negative 25 equals, 3x minus 7. If we add 7 to both sides, that's going to give us negative 18 equals 3x. So x equals, if we divide both sides by 3, we will get negative 6. So x is negative 6. All right, so we have our point negative 6, comma, and we need to find the y value. So we're going to substitute negative 6 in for either one of your equations. I would really recommend look at both equations and figure out which one's easiest. Whichever one's easiest to substitute that negative 6 into, use that. You can actually do it with either one. It doesn't matter. So let's do the top one here. So if x is negative 6. Y equals negative 6 times 11 is negative 66. Minus 7 more will be negative, 73. Yeah, negative 73. So negative 6 comma negative 73 is our solution. And we can check that by substituting it into the bottom one as well, just to make sure that works. But that's the idea there. If we look at the graphical perspective, we said the solution was negative 6, negative 73. Negative 6, negative 73. Here's 8, negative 80. Here's 60. So negative 73 is right there. So that point right there, again, graphically showing us that the solution is the same that we got algebraically. Okay, so I want to mix it up just a little bit now, and I want to give you a situation in which we don't have y by itself. So what we've seen previously is you're given us a system of equations with both in slope-intercept form. But there are times where we're given it in standard form like this. So both of these are in what we call standard form. All right, if you look at the graph, you can see the solution is right in here somewhere, maybe this is 2.5, so maybe 2.1 or something like that. The y value of that intersection point is maybe 2.7 or something, I don't know. Then that's the whole point I want to show you is sometimes it's difficult to see the solution graphically. It's not a perfect science here. We can't just look at that and tell. Obviously, if you're using Desmos, you can click on the point and see, but otherwise, we're going to need to do this algebraically. And that's what I wanted to show you today is the advantage of doing algebraic. We can be very precise in our algebraic solutions here. So To do this algebraically, we're going to actually do the same thing. We're going to use substitution. However, we're going to have to do a little bit of work ahead of time. So right now, we don't have y is equal to something or x is equal to something, but we can get it, okay? So figure out which one's easiest. So if I'm looking at my 4 variables, which one is easiest to solve for, to get by itself? And it's going to end up being this y or this x. Because those don't have any coefficients, so we're not going to end up having to divide or anything. All we need to do is subtract over the other term in that equation. I'm going to go ahead and go with this x here to show you that we don't have to solve for y, we could also solve for x. So let's go ahead and solve for x here. So if we do that, we're going to get x equals, subtract 4y from both sides. So we're going to get x equals 12 minus 4y, or you can do negative 4y plus 12. Either way is fine. So we know that x is equal to this expression right here. So therefore, we can take what x is equal to. X is equivalent to that. So wherever there's an x, we could put that. And that's exactly what we're going to do. We're going to take what we know that x is equal to, and we're going to substitute that into the x up here. So literally, we're going to, anywhere there's an x in this top equation, we're going to put negative 4y plus 12. So let's do that. 4 times x, and this is a major point right here. Always put that expression in parentheses. Okay, so we're going to put, I'll put it in red here, negative 4y plus 12 plus y equals negative 5. Okay, so again, if you left off your parentheses, you wouldn't be multiplying the 4 times the 12, and it would give you a mistake there. So always put what you're substituting in parentheses, and that goes for anything in math. Anytime we're substituting in, put it in parentheses, and then go from there. So we have 4 times x, this is x, right? As we see over here, x is equal to that. So 4 times x plus y equals negative 5. But the great thing about this, now that we've substituted in, is how many variables do we have now? There's no x's anymore, right? We only have y's involved here, so that allows us to actually solve for y now. All right, so let's go ahead and distribute the 4 out. So it's going to be negative 16y, and then 4 times 12 is 48, plus y equals negative 5. So we're going to solve for y now. So let's see, if we combine, because these are like terms, right? So negative 16y plus y, so it's going to be negative 15y plus 48. Okay, and then we're going to subtract 48 from both sides. So we're going to get negative 15y equals, negative 5 minus 48 is negative 53. And then we're going to divide both sides by negative 15. So that's going to give us y is equal to, let's see, negative 53 divided by negative 15 is 3.53. 3.53, and the 53 is repeating. All right, so from there we can actually substitute this into the other equation. So 3.53 with the 3 repeating, or we could just do 53/15. So I'm going to leave both of those for right now, and I'm going to see which one's easier to substitute in up above in our second equation. So we've been working with this equation, right, at the top. We substituted what we knew x was equal to in up here. So that means we've got the x value, or sorry, the y value, so we can substitute the y value in for either one. All right, so you can put 3.53 repeating here or there, either way. I think it would probably be easier to do Actually, probably equivalent here, but let's do the top one here. Okay, so if we substitute what we know y is equal to in there, we get 4x plus 3.53 repeating equals -5. So you could subtract 3.53 repeating on both sides. So in your calculator, I've got my number here, and what I can do is do -5 minus there, and then I can cursor up to that number there and hit enter, and it'll bring it down. So I can actually use the full number there as best as possible. So we're going to get -8.53 repeating, which makes sense because we're just these two make -8, and then you got the decimal there. And then we're going to divide by 4, right? Because we have 4x, so we're going to divide by 4 on both sides. So in your calculator, you can just hit divided by, and it'll automatically take the previous answer and divide it by 4. And then hit enter, and we see our answer there. So -2.13 repeating. Which our estimation was -2.1, so we were pretty close. Just looking at it graphically. So we've got the point -2.1 3 repeating, comma 3.53 repeating is the decimal versions of that. So -2.13 repeating, and then the y value is was it 3.5? Yeah, 3.53 is the y value here of that intersection point. So that point here is what we were finding. All right. So two things there. One is we can find the exact solutions algebraically, whereas graphically we couldn't. And the other one is I wanted to show you how to do one with both in standard form. So you just solve for one of the variables, substitute what that's equivalent to into the other equation, and then you can solve for the first variable from there. Once you get that first variable, you can substitute that known value into either equation, and there you go. You got your points. Or point, I guess I should say. All right, so lastly, I wanted to bring up this TN Ready type problem. We're going to do this problem during this lesson and in our next lesson, and you'll see some differences in our approaches in both lessons. So it says, at a county fair, Emily rides the spinning vortex 3 times and the gravity breaker twice for a total of 14 tickets. Troy rides the spinning vortex twice and the gravity breaker 3 times for a total of 16 tickets. And then it says Roger plans to go on the spinning vortex 4 times and the gravity breaker 5 times. How many tickets will he need? So we need to find out how much each of the spinning vortex tickets cost, and then how many needed for the gravity breaker. So let's take our first situation here, Emily. So we're going to come up with an equation for Emily. Emily rode the spinning vortex 3 times. So however many tickets it cost her to do the spinning vortex, we're going to multiply that by 3. So the V represents the number of tickets required for the spinning vortex. Plus, but she did the gravity breaker twice. So 2 times, we'll say G for gravity breaker. So the number of tickets for the vortex and the number of tickets required for the gravity breaker. And her total, so we add those together, we get the total amount it took, and that would be 14 tickets. All right, for Troy, he rode the spinning vortex twice and the gravity breaker 3 times. And that gave him, or required a total of 16. All right, so if we put these together and think about it as a system of equations, we can solve for V and G to find out how many tickets it costs for each one. Then we can go back to Troy's situation and figure out how many it takes for him. So what we need to do is we need to isolate one variable here. I'm going to isolate, it doesn't really matter here. All of them are probably equally difficult, but I'm going to isolate 2V, or actually end up V. So let's get V by itself here. So let's subtract 3G on both sides. So it's going to give us 2V is equal to negative 3G plus 16. And then divide both sides by 2. So I'm dividing the whole left side and the whole right side by 2. So and because of that, when we divide a fraction, we can actually divide both terms by 2. So over on the left, we're going to get V equals, and then negative 3 divided by 2, G plus 8. So we know that V is equal to this right here. So we can actually use that to substitute in for V in the other equation. And we're going to have to deal with some fractions here, but that's okay, right? We can work with fractions, not too bad. All right, so 3 times V. V is negative 3 halves G plus 8. Plus 2G equals 14. So we've substituted what we know V is equal to in for the V here. And now we've got 3 times V plus 2G equals 14. But now we've got an equation full of G's. So we can actually solve for the number of tickets it requires for the gravity breaker. Okay, so we multiply here. Let's see. We're going to multiply in here. Let's see, 3 times negative 3 halves. So really this is 3 over 1 times negative 3 over 2. So we're going to multiply the numerators and multiply the denominators. So 3 times negative 3 is negative 9. And then the assumed 1 that's under here, 1 times 2 is just 2. So it'll be negative 9 halves G plus 3 times 18 is 24 plus 2G equals 14. All right. From there, we can combine the G's. Negative 9 halves, and then 2. Well, actually, let's take a different approach here. Since we have a denominator of 2, what if we multiplied everything by 2? We can do that, right? As long as we multiply the whole right side by 2 and the whole left side by 2, we're okay there. So if we multiply the whole left side by 2, everything's going to get doubled. So, and the point of that is to get rid of this 2 in our fraction here. So that's going to be negative 9G plus 48 plus 4G equals 28. So we multiplied everything by 2 to reduce our fraction here so that we can actually solve it a little bit easier in our heads. So now we're just combining negative 9G and 4G, which is negative 5G plus 48 equals 28. So then we're going to have negative 5G, let's see, subtract 48 from both sides. So negative 5G equals, that's going to be negative 20. So when we divide by negative 5 on both sides, we get G is equal to 4. All right, negative divided by negative is a positive. So every gravity breaker ride requires 4 tickets. Okay, so then we come back up here to either one of these equations, doesn't really matter which one, and we can solve for the number of tickets for the spinning vortex. So let's do that up here at the top right here. So we have Troy, we're going to use Troy's equation, 2V plus 3G. We found out G, we solved for G, is 4, right? So put 4 in, equals 16. That's going to allow us to solve for the other missing variable. So it's going to be 2V plus 12. So 3 times 4 is 12, right? So we can subtract 12 on both sides. That's going to be 2v equals 12 minus, or 16 minus 12 is 4. So if we divide both sides by 2, running out of room here, v equals 4 divided by 2 is 2. So every gravity breaker ticket is has 4 tickets. Every spinning vortex is going to be 2 tickets. So now we can think about Roger. I said Troy earlier, but I meant Roger. So spinning vortex 4 times. So that would be 4v plus gravity breaker is 5 times. So it'll be 5g. And we want to know what the total is. The good thing about it is we know what v and g are now. V is 2, so we can put 2 in for v. Right? If it requires 2 tickets and that he rides it 4 times, it's going to be 8 tickets for the vortex. And then 5 times for the gravity breaker, and each gravity breaker is 4 tickets. So it's 5 times 4, it's going to be 20, giving us a total of 28, which is C. All right. So as you can see, this one was pretty tedious. A lot of work to be done on this one because it wasn't necessarily that easy to solve for one of the variables. When we solved for v starting out, we were going to have to divide by the 2, and that gave us some fractions, and so it made it a little bit more difficult. In our next video, we're going to talk about a different way to solve these systems of equations that might make this problem in particular a little bit easier. So you're going to have to decide on your own, and this is just going to come with some practice and time, is figuring out when is substitution better, when is elimination better, or can I just graph it and see graphically what the solution is. All right, so we're going to have those 3 solution methods that we're going to look at. But our goal for today was simply looking at substitution and using substitution to solve a system of linear equations. All right, so hopefully you'll join us next time for something called elimination and looking into how to solve systems that way. We'll see you then.